So we are going to talk about the enhancements to the REST API gateway. And I guess before I jump in, and it's probably a good idea to step back and give a brief introduction to the REST API gateway in general. What's the gateway, what it does, and what role does it serve in the Kaleido stack? And feel free to interrupt me at any time with any questions. We also have our CTO, Jim Zhang, here. So if you want to post any questions on the chat, one of us will be happy to answer your question. So let's get started. So I'd like to cover a brief introduction and then talk about some of the improvements in specific. And then there's a few of them. So let's go over some of the introductory concepts to a REST API gateway. So what's the REST API gateway and what role does it serve? So basically the REST API gateway is a web and messaging API, which is positioned in front of Ethereum nodes, and it takes the hassle out of submitting transactions to an Ethereum node. The Ethereum node, as you're all aware, provides a native JSON RPC interface to submit transactions. And there's a lot of things which need to happen before a transaction can be submitted to Ethereum, let alone the fact that the format of submitting these transactions is pretty bespoke. So some of the things that need to happen offline or out of band is your smart contract is written in Solidity, so it needs to be compiled. There's types on the Solidity contract which all need to be in the right shape and form. And before the contract or the transaction is submitted to Ethereum, it needs to be encoded in a particular format which is accepted by the Ethereum node. And this is called the RLP encoding, which I'm sure you all are aware, which is the recursive length prefix encoding. The next thing to be aware of is the transactions in Ethereum are mainly asynchronous in nature, which means we submit a transaction and then we get a receipt after a second or two, and then soon after that we need to keep polling for the status of those transactions to see whether it's been mined into a block. And this poses an interesting challenge in terms of any external systems which are not conversant with this kind of paradigm. The primary function of the API gateway is to address some of these friction, so to say, in terms of submitting transactions to Ethereum, and making sure that this is a smooth experience for anyone who's interacting with an Ethereum node. So aside from solving all of these specific challenges like compilation of the Solidity code, the ABI type mapping, the recursive length prefix encoding, the gateway also supports transaction receipt polling. We provide a receipt store, which has the ability to store receipts for all the transactions which are submitted via the gateway. And you will also see, as we talk about in this presentation, that the gateway is very, very good at supporting a high throughput transaction submission. There's also some nice built-in features such as concurrency management and nonce management. We'll go into the specifics of each of these options. But basically, it provides an integration bridge for Ethereum permission chains. So there's a web service and there's also a messaging interface, which means external entities can get notified about events and logs which are emitted from smart contracts. And the process is as simple as configuring what is called an event stream and tying it to a subscription, which is basically an external webhook onto which notifications can be sent. So a lot of power packed into the REST API gateway, and underlying the the gateway is a messaging infrastructure which is built on top of Kafka. And basically there's, like I was saying, there's the messaging part of the interface and then the webhooks part of the interface. And as you can see in this diagram, the Kafka messaging tier is basically the underlying backbone to the REST API gateway in terms of the messaging layer. The gateway obviously does a great job of consuming messages from Kafka and then ensuring ordering for the messages in terms of what's submitted onto the node, and then provides certain other services like receipt management and nonce management and so on and so forth. Any questions so far? So the other thing I'd like to note is not only is the interface a nice REST API interface, there's also a bundled a user experience which is Swagger based, which we'll go through shortly on the Kaleido console. This makes it pretty intuitive and easy to try out your smart contracts and submit transactions to nodes on the Ethereum network. So with that said, let's go over a brief demo of what it's like to use the gateway. And I guess we'll start with a simple example of using token deployment onto a Kaleido node. I've set up a demo environment here, so we don't have to spend time going over the entire setup. But what we'll do today is deploy a digital asset, which is basically an ERC20 token. And then using that, we'll explore some of the options provided by the Swagger interface and then go over some of the other features. So I see a question posted. What are the number of transactions and smart contracts that can handle using the RESTful APIs? So are you referring to what kind of contracts can be deployed using the RESTful APIs? So basically the gateway supports the ability to upload your own smart contracts, and you can find a lot more demos and documentation on the Kaleido website. But the way this works at a high level is there's something called a shared project for a contract. So you create a contract project at your consortium level, which is either one or more smart contracts. And then once you have a collection of smart contracts into a contract project, that can be deployed and promoted to individual environments within your consortium. And once those contracts are deployed to an environment, then pretty much all the exposed interfaces as part of the smart contract can be executed as part of the API gateway. So the gateway provides a RESTful interface for all the methods in the smart contract, which means they are now a matter of invoking REST APIs using Postman or some other scripting mechanism that you prefer, or whatever your favorite programming language is. Right. So if there's a follow-on question, feel free to post it. In the meanwhile, let's go on to deploying a token contract. So what I'll do here is deploy a standard ERC20 token. And for this, I'm going to pick one of the node wallets as the signing account. Now, if you remember, any transaction which is sent to Ethereum or any contract which is deployed needs to be signed by a particular account. And I'm going to pick one of the node accounts as the signing account. And we'll use our token factory, which provides some nice predefined templates. We'll use the ERC20 mintable burnable in this case and deploy this token contract. Can we also, so we have another question. Can we also deploy a contract through the API gateway by submitting the compiled bytecode and ABI? Absolutely, yes. And maybe after this, we can go over to the contract management page, since there seems to be some interest on that front. And yes, we do provide an option to upload your own compiled bytecode and ABI. And that can be one of the compilation methods in a contract project as well. And obviously, after compilation, it can be promoted to one or more environments. Should take a few seconds to deploy this contract and come back with a contract address and all of that good stuff. Okay, so we have a contract for the ERC20 deployed. And what we will do now is we will now deploy an instance of the contract using the Gateway API. So let's call the token name as test with a symbol, and we will deploy a token instance. So what this is doing is creating an instance of the contract. And you can see here that the Gateway API has now provided a nice path, which forms like the root URL for all your contract methods. And once we exit out of this screen, we will now see that there was an instance deployed, which, let me close. Yeah. So we can view the instance API. And the instance can be scoped to any of the nodes that we want to submit the transactions on. So this brings us to one of the improvements I would like to speak about here. So previously, if you've used the API gateway, the experience was that a new tab would be opened with the Swagger interface with the instance of the contract. Now you can see it's nicely embedded into the page that we are viewing, and it allows you to try the different methods of the contract within the same page. So these are standard ERC20 functions within the contract. So what we will do is maybe try transfer of tokens to an address. And there's an option to try out any of the functions within the contract. And we provide a nice template as to what the parameters must be for the invocation. And there's a bunch of options which you can specify as request parameters when sending the request. The main thing I'd like to highlight here is there are two methods of submitting transactions to the API gateway. One is the synchronous method, in which case the gateway makes sure that the transaction is mined on the node, waits for the receipt, and then returns that response back to the user. Now that's obviously synchronous, and no receipt then is stored on the receipt store, which I was referring to earlier. Now, the true power of the API gateway is using the asynchronous submission of transactions, where you can submit hundreds and thousands of transactions into the gateway. And the gateway does the job of managing the receipts for each of these transactions and then updating the status of the transaction once it has been mined into a block. we'll see as part of the configuration parameters for the gateway. But once we set a time limit for how much time the gateway needs to wait before a transaction is mined, it makes sure that the receipt status is checked and updated in the receipt store. So for now, let's try the synchronous method of the transaction submission, because we want the status to be updated in our response, since I'd like to show you the response and the request. And what I'm going to do here is use the address from another node. So we'll be transferring tokens to one of the other nodes in the same chain. So I'll use node 2's account address. And obviously, if you have any other address you want to transfer the tokens to, that's a perfectly valid option. My mouse is having battery issues at just the right time. Okay. Are you all still able to see my screen?
Yeah, we can still see it.
Okay, great. So I just switched one of my monitors because I need access to the mouse pad. Okay, so I'm going to enter the recipient address here. And send this transaction. And I've set the sync mode to be true, which means this will be a synchronous transaction submitted to the node. Okay, so we see that we got a 200 response for this request. And you can see we've not dealt with any solidity at all so far. We haven't dealt with JSON RPC and any of those, transaction encoding. None of those complexities involved here. It's a matter of invoking the REST API, and this the Swagger interface also provides the actual request which was sent. So obviously, if you want to try this out of band, or if you want to use the request in any of your scripts, this is one way to get hold of the request. But obviously, our documentation provides like generic guidance on how to form the requests and what to check for and stuff like that. So we can see that the transaction was a success, and the appropriate number of tokens was transferred to the address that was specified, and all of this is nice and easy REST APIs. Okay, looks like there are no more questions so far, so I'll keep motoring along.
Hey, Vino, just as you were speaking, the new question popped up.
Oh, okay. Let's see. Okay, the question is, I have tried using the Swagger page on my contract, and a simple call to get balance seems to hang forever. Cancel is red, and calling the same method from Postman works okay. So my first gut reaction is this should not happen, but if you could create a support ticket from the page you're at, so if you scroll down all the way to the bottom of the page, or maybe it doesn't show up in Swagger, but any other page, you should be able to say contact us and create a support ticket, and we'll be happy to take a look at your environment, Marco.
That should be the question mark button on the left nav.
Okay. I'm sorry, I missed that. Yep. So this would be the way to hit contact us, and from here it will give us the coordinates of the page you are at, and help us find your environment and node. Okay. So let's jump back to one of the other topics that seemed to garner quite a bit of interest, which was the way one would create contract projects and what are the different methods for uploading your Solidity source code. So under the consortium, if you click on shared assets, there is something called contract projects. And this is the starter or the starting point for creating your, creating a place where you upload your smart contracts, or you create your compilations and then promote it to the environment and start using the REST gateway. So while we are at this, I'm going to use an existing project, or maybe let's create a new project to walk through the details of what it looks like. So I'm going to create Ethereum as the protocol, and and this is something I'll be demoing a short while later, so I'll piggyback on this opportunity. So as you can see here, there's a few options to upload or bring in the contract code. The first one is something called a managed compilation. So if you point the contract project to a GitHub repository, which obviously should have access, and Kaleido does the job of retrieving the code from the GitHub repository, compiling the smart contract, and then forming a contract project which can be promoted to an environment. The second option is to upload the source code and compile the contract using an interface which is provided by Kaleido. Or if you already have a precompiled contract, so let's say you have an ABI and bin file, and you would simply want to copy paste the ABI and the binary, then, and the dev docs, of course, we provide the option to bring in a precompiled contract as well. And since Kaushik was asking specifically about precompiled contracts, let's go over how you would add a compilation for a precompiled contract. So I'm going to click on a new compilation, and then the scope of this compilation is going to be the membership. So obviously any nodes or services within the membership will have access to this contract project and the source compilation. And let's give this a name or a description, which I'll name as V2, because I'm going to talk about the ABI encoder V2 format, which was a recent enhancement to the allowed Solidity formats. So as you all are aware, one of the things that's been added as an enhancement in Solidity is the ability to use structures. And if we, so let's look at the contract code here. And the thing which is allowed as part of an experimental ABI encoder V2 format is the ability to use structs in your Solidity source code. So I'm going to demo using such a example Solidity file, and then uploading this or adding this to a contract project as a precompiled contract, and then promoting that to an environment and using the Swagger interface to to interact with the contract. So nothing fancy here, basically an example of two structures, and then we are going to instantiate the contract with one of these structures, and then get the type of the sender. So I'm going to compile this contract, and this can be done offline if you're if you're uploading a precompiled source code. And you can see that there are two files generated here, which is the ABI, which is the application binary interface. And the second one is the actual binary. So what we'll do here is paste the ABI and then paste the bytecode separately. I might need to cat this file so it's easier to copy paste. Maybe not. Is it the same one? Yep. That's it. So one thing to note here is the contract bytecode needs to be prefixed with 0x, just for it to be a valid hex string. So we have now compiled or uploaded a compiled version of the contract. And you can see that the UI now shows what is called the environment promotion status. And this contract hasn't been promoted to any environment, which would then make it into an actual gateway instance and ready to use. So let's promote this into the environment we are working with today. And we will provide a friendly name which would form the part of the API gateway path. The next thing is to deploy an instance of this contract. So we'll deploy this to node 1. And you can see here that the Swagger provides things like what are the constructor inputs, right? So if you were to deploy this contract, what sort of arguments do you need to provide to the contract? So let's form so let's look at the constructor. Oops. Did I stop sharing there?
Yeah, we can see your sharing more.
Okay, hang on. Something's happened with my my screen. Is it? Okay, let me try this again. Yep. Can you see my screen now?
Not yet. Okay, now we can see it.
How about now?
Yeah, we can see it now.
Okay. Sorry, my mouse is behaving odd today. And obviously I don't want to reboot my computer now. So I'm going to have a nested structure here. And let's try to deploy this contract. Okay, so it looks like I'm missing some parameters. So I need a val1. And we have str1, str2, address1, and a byte array. Okay. And let's use the node's address here, just for convenience, and then okay.
Hey, you need a few more commas.
Yep.
One more after test one.
Thank you, Jim.
I think that's all.
Just a few. So saying supplied value nil could not be assigned to adder one. We're sending type 1.
I think the name should be adder1 instead of address in your payload.
Sorry about that. Should make it better. Okay. So we have a nested contract instantiated. Well, a contract with nested struct instantiated here. And as you can see, this is using the ABI encoder v2 format. So that's a quick example of using structures in your Solidity source code, which is now supported as part of the REST API gateway as well. Any questions so far? Okay. So we obviously created an API gateway and we instantiated it, and then we promoted it to an environment. And we also saw the different ways in which the contract project can be compiled, which is either using a GitHub URL, which has the smart contract code in it, or using a precompiled option, or by uploading the Solidity source code directly. So the next thing I'd like to talk about is certain customizations which can be made to the API gateway to make it really, high performant depending on the use case. Obviously, the standard configuration for the API gateway suffices in most use cases. But if there's any need, or if there's, depending on the use case, if there's a requirement to meet certain higher throughput numbers, the API gateway allows us to configure or tweak the settings for the gateway, which allows us to to be able to push a lot more transactions through the gateway and onto the node. So let's walk through an example for what is called a protocol configuration to tune the API gateway. And we'll use the example from node 1. So I've already got an example here, and I'm going to edit this, or maybe let's just start with a new example. So we'll add a new protocol configuration. And let's call it a tuned gateway. And if you scroll down in the section on protocol parameters, so obviously we discussed, for anyone who's attended previous Tech Tuesdays, we discussed some of the other protocol configuration parameters in a previous session, so I won't touch upon any of those. But what we'll do is focus specifically on the API gateway customizations today. And there's a few things which can be configured in the asynchronous mode for the API gateway. So the main thing that comes to mind when we talk about what impacts the most in terms of throughput is, one of the key aspects is what is called nonce management. As you all know, every Ethereum transaction is submitted with a nonce, which basically tracks the number of transactions which are submitted from any account. And the nonce basically has two purposes. So the first is to track how many transactions are submitted from an account. And the second thing is to provide a protection against replay attacks. So you don't want to submit the same transaction twice. And what that means is you want, or the way to avoid that is using the nonce. So the gateway provides some extensive functionality in terms of nonce management. When you rely on the Ethereum node for nonce management, what that means is we are relying on the TX pool and the Ethereum code functionality to return us a nonce, and there's a way to query the transaction count on any particular account. So once you query the transaction count, the nonce for the next transaction is typically the next nonce which is to be used. Now that's all fine when you're submitting transactions to the node in like a normal pattern. But when you want to send requests in a concurrent manner to a node, mainly for like throughput considerations, the gateway allows us to configure concurrent submission of transactions to the node. And when concurrent transactions are submitted to the node, one of the nice aspects in the gateway, which is a recent enhancement, is to also perform the nonce management on the gateway. What this means is when you're submitting transactions to the gateway, they are submitted in a particular order by your app or by whatever third-party system which is submitting transactions. And typically the expectation is that those transactions are submitted to the node in the same order. So in order to ensure this is the case, the gateway has the support for managing nonces. And this becomes more important when you configure the concurrent submission of transactions. So the way you would configure concurrent submission of transactions is by configuring what is called send concurrency. And the other hook that we provide is something called the max in-flight transactions, which basically governs how many transactions can be packed into a block. And we've easily packed, in real customer networks, 1,000, upwards of 1,000 transactions within a block. Obviously, it depends on, how much gas each transaction consumes and what's the gas limit on the block. But, the gateway is highly performant. Obviously, it depends on things like what size nodes do you have, but assuming we have the right set of conditions, we've seen, some pretty impressive throughput numbers through the gateway when sending transactions to the node. So the first thing you ought to configure is what's the maximum in flight. I'm just picking an arbitrary number here, but obviously, you can pick a different number. But this governs the maximum number of transactions which can be packed or which will be packed into the block when sending via the API gateway. The second thing we are going to configure here is what is called the send concurrency, which is how many requests can be sent in parallel or how many requests are sent in parallel to the node. Now, remember that when you submit transactions to a node, there might be some operations like calculating or estimating the gas. So typically one of the API calls that precedes the actual submission of the transaction is to perform the gas estimation via a separate call. And once the gas estimation is performed, and then, typically if you're using a fat client like Web3, there's a call to get the nonce for the account as well, because that needs to be included in the request. So once you are making all these calls, it means that the data which is getting sent to the Ethereum node and the processing which has to happen on the node, it takes a finite amount of time. So there's typically an upper bound to how many transactions you can send concurrently and what's the maximum number of transactions you can pack into a block, because you need all those transactions to be mined and included and ready for processing into the transaction pool within the time the next block is to be cut. So there's that way there's a theoretical upper limit to the number of transactions which can be mined into a block. It's governed by how much gas is consumed by a transaction and how much time it takes to mine the transaction. So I'm going to enter an arbitrary number here, which basically dictates how many concurrent requests can be sent to the node from the gateway. The other thing which the gateway allows is throttling of the requests at the Kafka layer. And the way this is done is by configuring the flush frequency, which is how many milliseconds do I need to wait before I'm going to batch all the requests to be sent to the node. And I'm going to pick 500 milliseconds here. And we can also configure how many messages we want to wait for until all the messages are bundled together to be sent across to the node. So maybe let's configure both as 50 here. So 50 messages, and we are going to wait for 50 milliseconds before we batch all the transactions. We want to pick the ability for the gateway to manage the nonces, because especially when transactions are sent concurrently, the gateway has logic built into it to say, if these requests or if these transactions are getting sent from the same from address, the gateway has the intelligence to then say, what's the starting nonce? And then what are the other nonces which need to be assigned to all these transactions, depending on the order in which they were submitted to the gateway. So that way, you're guaranteed to have a particular ordering between all the requests or between all the transactions, and it can be sent across to the node. There's another feature, and this is a very like a pretty advanced feature, which I'll talk about in a bit, but it's what's called as the gap fill transaction. And there's a setting here to say, hey, gateway, attempt a gap fill transaction when a transaction that has been submitted to the node fails before it's being mined into a block. And we'll talk about this in a minute, but this is one of the advanced settings that you have the ability to configure as well. So once we create this protocol configuration, it initially shows up as inactive, which means it hasn't been applied to a runtime yet. And what we'll do is attach a runtime to this, which I'll pick in this case node 2. And we need to apply the configuration to node 2. This basically resets the node, which means the node gets restarted with the appropriate configuration for the gateway parameters. And once the node comes back up to a started state, we will be ready to start submitting transactions. So while the node is coming back up, and it just changed its status to applied, sorry. Let's go over the details of what exactly a gap filling transaction means. So let's first look at what happens in case of parallel submission of transactions without gap filling. So I've got the gateway on one side here and the node on the other side. So when you get, and we'll take send concurrency of 5. So we can submit 5 transactions in parallel. Once you get transactions, they're processed by the gateway and submitted onto the node, where it goes initially into the mempool of the node, which is basically the transaction queue on the node. So let's say we submitted 4 transactions, and there can obviously be transactions from other accounts as well, which are color coded here for demonstration purposes. So all the transactions with the green background, they're from a particular node, from one account, and all the transactions from the other accounts here are displayed with a different color. So let's say transaction 3 was rejected before it could make it into the pending list. And there's, one of the ways that this can happen is, for example, if there are insufficient funds on the account, if you're trying to do a value transfer. So if you're trying to transfer 100 Ether when your account balance only has 10 Ether, then that gets rejected by the Ethereum transaction processing logic, very early on, because it sees that there's not enough balance. Now, if such a rejection occurs and you subsequently receive a new transaction on your inbound queue on the gateway. Now, without gap filling, what happens is that the gateway is going to look at the nonce on the account, and it's going to say that there's only been 3 transactions submitted with this account, and obviously it doesn't take into consideration the failed transaction because that wasn't that did not take up a nonce, which means that the new transaction is now submitted with nonce 3. And what happens then is you've got a situation where there's one transaction which is out of order. So this transaction, which was submitted after 4, the end user would probably expect that it gets mined after 4 or gets included after 4. But because of the way we had a failure in one of the earlier transactions, it's going to show up on the chain in an out of order sequence. Now, how does the gateway solve this? So the gateway attempts to solve this by using a technique called gap filling. And we can see here, the same scenario play out. So we had one of the transactions which failed. But with gap filling, what the gateway is going to do is it's going to fill this failed transaction with a dummy transaction. Now the dummy transaction is going to be like zero value transfer, which means it has no effect on the account balance or anything like that. It's going to attempt to gap fill the transaction by submitting a zero value transfer transaction, which means the sole purpose of that gap fill transaction is to occupy that nonce so that any subsequent transactions which were submitted will retain the same nonce when they are processed by the API gateway. Did that make sense? Okay, so there's a question here, not exactly related to what we were just talking about, but it says, how does the gateway architecture fits into the AWS gateway or the VPC architecture? So I think there are two fundamentally different concepts. The API gateway is something which is co-located with every node within the environment in Kaleido. And obviously the AWS gateway or the VPC architecture is something which is at the cloud infrastructure level in AWS. And I'm happy to let Jim elaborate if you have any thoughts to add, Jim.
Yeah, sure. I'm assuming AWS Gateway is referring to the API gateway that you can use to do rate limiting and manage tenants' access to your API. So that's a very different layer in the architecture stack that tends to sit on top of your deployment in AWS. That's sort of the first layer of API management that any access to your system deployed to AWS will hit. The API gateway Vinod has been talking about is much deeper into the architecture stack that's like very close to the very bottom where the blockchain sits. And that's immediately in front of the blockchain nodes that regulates how transactions in particular are submitted to the blockchain. So besides providing a convenient interface so you can just do REST and JSON to submit transactions to Ethereum nodes, it also provides these advanced tuning parameters for performance-related behaviors. So yeah, and you should be able to use both at the same time. AWS Gateway will regulate on the very top, and that's every APIs that your system provides. And then API Gateway in Kaleido in particular is when your application needs to access the blockchain node itself. VPC architecture, maybe we should have a private conversation about this and see what in particular are you referring to with VPC architecture, and we can exchange some messages in the Q&A panel. So Vinod can continue with his presentation.
Okay, so that brings me to the end of the things I wanted to talk about, which I think I covered most of the enhancements which we've recently made to the API gateway. So I don't know if there are any follow-on questions. We are also at the top of the hour. So if there's any questions, I'm happy to answer. Otherwise, do feel free to reach out to us anytime if you have more detailed questions about the API gateway, or you would like to understand how to tune your specific environment and the gateway which is deployed in it, and we'll be happy to assist you in any customizations. Okay, so unless there are no more questions, okay, so I think there was one more question. Okay, so that's more of a comment than a question, I guess. Great. Thank you all for attending, and do reach out to us if you have any questions or follow on. Otherwise, we'll see you in the next Tech Tuesday. Thanks all. Bye.